Hi everyone. So this video is going to be a short video and recap about alkanes and their reactions to help you aid in your AS level chemistry alkane questions. Now, let's get started into it, okay? So the first thing about alkanes is that I'll be recapping from the very general and basic part of it, for example, from O levels, a little bit from O levels. So about alkanes, you know how alkanes have a general formula of CnH2n plus 2. And just like all the other homologous series, they increase by a CH2 group down the series, right? And also that they have carbon to carbon single bond, which is sometimes considered not to be a good information to dedicate itself as a functional group because everybody has carbon to carbon single bond. Alkanes are not just unique to it. That's why we usually say that alkanes are not that reactive. So carbon to carbon single bond is everywhere, even though it's a part of them and it's a representation of them. So we do call them functional groups sometimes. But then again, this functional group is not that unique and doesn't let it react as often as alcohol or alkene would do. So therefore, this functional group is not something very useful for alkanes. Alkanes are very much inert. Now, why are they inert? Why can't they react as much? That's because in order for the chemicals like organic chemicals to react, they must have either electron density region or they might have a polar compound around them because they are very much saturated and they're bonded strongly with their counterparts, as in like hydrogen and carbon. They're pretty much bonded in a very stable manner. Carbon to carbon is also bound in a very stable manner. As a result, when any kind of chemicals like chlorine, bromine, iodine, water, let's say any other chemicals comes in, if they can't bond with them because there isn't enough polarity difference in the alkane, and the fact that they're pretty stable because of the single bonds they have formed right here. That's why they don't want to react with anything incoming unless you give that incoming species a little bit of activation energy. So in this case, we know that given that alkanes are very stable, they will not work without an activation energy. So what kind of reactions do they do? Are and how do we make alkanes pretty useful to us? Well, alkanes, in for your AS level chemistry, it does only two reactions. One reaction is combustion. And I'm sure you guys are well aware of what combustion can do. Well, combustion is nothing very difficult. It's basically burning any kind of hydrocarbon. And whenever you try to burn hydrocarbon or alcohol or let's say carboxylic acid, anything organic, it always gives you CO2 and water if you, let's say, provide here enough amount of oxygen. Only then that can happen. For example, in this case, I'll write something, I'll use a beer alkane in this case. So for instance, let me write here octane. C8H18 plus O2. If it reacts with in the abundant supply of oxygen, it's going to give you carbon dioxide gas and it's going to give you water. Now, if you balance it up properly, you'll see that it uses 2 moles of octane for 25 moles of oxygen gas and 16 moles of CO2 to provide you with 18 moles of water. This is complete combustion, where you have added enough and abundant amount of oxygen gas in order for it to burn and form these two guys, carbon dioxide gas and water. Now, this guy is bad for us because it does global warming. How? Well, you know how carbon dioxide gets into the atmosphere and gets to trap infrared radiation, and infrared radiation can escape out of the atmosphere, and as a result, it traps back and reflects back into the Earth's surface and makes it warmer. Polar ice caps melts, our sea level rises, and a lot of other things happen. All right, now, what if you don't decide to put enough oxygen to the octane? Let's say you are trying to burn a hydrocarbon, but the oxygen availability is not as much. So when you don't have enough oxygen, you don't really produce a lot of carbon dioxide gas. You produce something called carbon monoxide, and then you produce water. But since you're using limited oxygen here, So it's gonna be 17 moles, and this is gonna be 2 moles, and if you balance it out, it's gonna be 16, and this is going to be 18. Well, in some cases, in some reactions, you will also find, it's very rare, but in some reactions, you'll find that the incomplete combustion also produces something called carbon. This carbon is dedicated to be set as a soot. Okay, it's a very sticky form of a carbon. And it usually settles on plants and it allows them to not do photosynthesis because it's like a very, very sticky pigment. So you know how when roadside, around the main roads and on the pavements, there are like lots of plants for some kind of reason. So those plants, if you ever come close to them, you'll see that there's a very thick layer, a very, not a thick, I'm sorry to say that, a very thin layer of black sticky film is actually present there. And that's basically the carbon soot, which allows them to not respire or not even photosynthesize properly because it creates a blockage. It's a very sticky form of a carbon that is produced whenever you do incomplete combustion with your, or for example, your alkane in this case. But this guy, carbon monoxide, how can we forget about it? I mean, carbon monoxide is impractically one of the most problematic gases there can be. Now, carbon dioxide is problematic too, but it causes a very long-term effect, and that's global warming. Carbon monoxide, it replaces oxygen from our hemoglobin, leading to asphyxiation. So whenever they'll ask you, what does monoxide do? You're not a bio student, so you don't have to say asphyxiation or removing O2 from hemoglobin. You can just go on and say it's very toxic to human blood, or you can say it's a toxic gas, okay? So this gas right here is pretty toxic. That's all you have to say. What is this? This is incomplete combustion. All right, so this was the first reaction that the guy, alkene, really does. And the next one it does is free radical substitution. Now we'll move to free radical substitution. I mean, I like free radical substitution. It's not bad. It's a good reaction. Well, let's get back to free radical substitution. All right. I don't like white surfaces. I like blackboards. I don't know why I like blackboards, but I do like blackboards, so I'm gonna make this black. I hope you guys don't mind. Someday I'll try to get the whiteboard also of some use, maybe. Okay, anyways. Now let's talk about free radical substitution. All right, free radical substitution is easy, but you have to learn it like step by step. That's when it gets easier for you guys, okay? Free radical substitution is, for example, let's say you have here what we have learned in our O levels is that we have learned that, let's say you have methane and you try to react it with chlorine and you give here UV radiation and you get CH3Cl and HCl. Since one of the Cl gets replaced by one of the hydrogen, and we say it's substitution reaction, but we never called it free radical back then. Now, how does that really happen? And is this the only product that we get? No, no, dear. No, dear. We don't get this as the only product over there. Well, alkanes do undergo free radical substitution in which hydrogen atoms get substituted by a halogen. And we're not new to this concept. But what's new is, since I said that earlier, alkanes are very unstable, they're very stable and they're very inert and they don't want to react as much. They can do combustion, and if you don't provide them activation energy, they will never, ever, ever react. So, what is the activation energy? Well, ultraviolet radiation is coming from the sunlight, and you can use ultraviolet radiation. This acts like light, this is a light source. It acts like a light source that tries to break down the halogen bond. And when the halogen bonds break down, with the help of light, we call that kind of reaction photochemical reactions. Okay. So what happens is the entire reaction happens in three stages. So I'll first dedicate the first step to be initiation step. Now, what happens in the initiation step? It's very simple. You bring chlorine gas, okay? Chlorine is single bonded with another chlorine. Well, when we say single bond, that means one electron from this chlorine has been shared with the other electron of this chlorine. You know, this chlorine also has its 7 electrons as well, and this one also has its 7 electron as well. Nothing happens to these 7. Now, what happens is when you put here UV radiation, a powerful high frequency UV radiation coming in, because UV lights are pretty frequency, have a very high frequency. And remember, it's not like an extra knowledge and extra information for you guys, but energy of a light depends on the frequency of the light. If you're providing a very high frequency light, the energy of that light will be pretty high as well. So when a high energetic light has been projected on the bond, this bond kind of breaks down. And when it breaks down, a chlorine receives its own electron, and the other chlorine also receives its own electron. But this guy electron is not paired anymore. So we call this guy, this guy as in the chlorine that has an unpaired electron is called a free radical. Any guy having an unpaired electron is a free radical. Okay. Now free radicals, they are very, very, very hungry for other elements to come in and join with them because they're very unstable. They're not good. I mean, they're very reactive. They don't want to stay however they are. They want to fulfill their necessity of having that extra 1 electron, and they're very, very, very going to be desperate about it. And they're going to take it anytime sooner they get a compound. Now that in the first step you have created free radicals, you don't create, okay, so another confusion is when you have a bucket of chlorine gases, it's not necessary that all of your chlorine gases at the very same time become free radicals. Some of them will become free radicals, some of them will remain as chlorine gas. Depends on how much abundant supply of chlorine gas you have given in the reaction, all right? So for the first part, you just need to know that some of your chlorine gas will get dissociated using UV radiation into free radicals. Now, the second step is the main game changer, guy, propagation. Propagation step is not that complicated because propagation steps, for example, they're here. What does propagate means? Propagate means continuation. Okay, so with the help of energy. So what happens is you have, let's say, methane, and you got here a free radical. As I said earlier, free radicals are hungry species that wants to fulfill their necessity and they want to take away whatever element there is nearby. So here hydrogen is nearby and hydrogen is easier to pick up, and free radicals are practically, they need 1 electron to fill it up. Therefore, they're going to take hydrogen to form HCl. Now, if you are taking one of the hydrogen from the carbon, I mean, if you're taking one of the hydrogen from the carbon and you can't just take hydrogen ion from here, you have to take a hydrogen with its own electron because you need to fulfill that extra electron necessity over this chlorine. So this guy, the carbon, it will have 3 hydrogens here, but one of the hydrogen will be gone and it will be left with a one single electron, again an unpaired electron. So it's going to be CH3 and representation of 1 electron being unpaired in carbon. So you have created another free radical. Now, the free radical here will not stay quiet. It's going to react with available chlorine to form CH3Cl. And again, you're going to form here a chlorine radical. This is going to keep on, this is going to go on for a longer time. And it depends on how much chlorine to how much chlorine your free radicals are there in the reaction, okay? Now, what happens is if, let's say, if you don't have as much, it might stop here. But let's say you have a lot of it and then what are the reactions happening. So this part that you've seen right now in part number 1 and 2, this is the first step of the substitution. The second step is this chemical right here will again react with a free radical. What happens when free radicals are reacted? They always take away the hydrogen. So this is going to take the hydrogen away, and you're going to form here CH2 and Cl. Now, CH2Cl radical will not stay quiet. It's going to react with chlorine to form what? It's going to form your CH2Cl2 and a radical. Now, do you think this radical will stay however it is? No, it's not going to stay however it is. Wait. So in the fourth part of the reaction, what you will be seeing right now is, give me a minute. So the fourth part, in the third part, we have seen that CH2Cl reacts with Cl2 gas to form this chemical. And in the fourth part, we will see that CH2Cl2 will react with the radical itself. And this again radical will take away the hydrogen and it will form CH radical with Cl2 HCl. This guy is not going to stay quiet. So CHCl2 radical will react with the leftover chlorine to form here CHCl3 plus Cl radical. And the last part would be where the CHCl3 radical will react with, CH3 compound will react with a chloride radical all over again to form a CCl3 radical with HCl. And this radical will react with chlorine to form here CCl4 plus a radical. So as you can see in the first step, CH4 was reacting with a radical to form here HCl. Every time the radical is there, it's going to crave for the hydrogen, it's going to take away the hydrogen. And you're going to be left with the compound hydrocarbon radical. And the second step, the first step, the chloride radical takes away the hydrogen. And in the second step, the alkane radical takes away the chlorine. You see, this keeps on repeating itself. First, chlorine radical will take hydrogen. The second step, alkane radical will take the chlorine. So this keeps on happening until you form CCl4. Now, a lot of you might ask, does all of this product have to end up being CCl4? No, 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 dear. This reaction can stop at any stage, 1, 2, 3, let's say 4 or 5. It can stop in any stages. However, the stoppage depends on the availability of chlorine gas you have in the reaction in the first place. All right. So this is propagation. And after the propagation step, you have created compounds. The last step is your termination step. What is the termination step? Termination step is pretty simple. In the termination step, what you do is you basically keep on forming whatever free radicals that you have formed in your what's that called, propagation step. They keep on combining to form a compound. Let's say you had alkyl radical and you had like a chlorine free radical. They combine to form CH3Cl. You had like 2 chloride radicals. It forms Cl2 gas. If you had like 2 CH3 radicals, they would form you C2H6 compound. So in the termination step, every radicals combine with one another, leftover radicals combine with one another to form products. So that's why in the free radical substitution reaction, in the 3 steps, just because of propagation step, you might have different kinds of products and in different amounts. It's not necessary that every single time you're going to get the same amount. All right? Okay. Now, the last thing about alkanes before I end this video is I'm going to talk about a very little bit about your crude oil and cracking. Because this is in your syllabus and you should know a little bit about it. There's no harm in knowing a little bit about it. So we do know that all the hydrocarbons that are generated, crude oil is a mixture of hydrocarbon containing alkanes, cycloalkanes, arenes. Those are basically benzene ring compounds. And they are extracted from the earth in the drilling process and a transport in oil refineries, right? We do know that. However, how do you really obtain the alkanes? So as you know that most of the time when the crude oil is like extracted from the seabed, we heat the crude oil. We heat the crude oil around like 330 degrees Celsius. And then we put it in like a fractionating column. There's a fractionating column that we place it in where we have like different fractions available to collect them. And yeah, at the very top, the temperature is around like 25 to 30 degrees Celsius. Here, we collect the most lightest gases of hydrocarbon, and that's basically refinery gas. Then we have gasoline, we have kerosene, we have diesel, we have fuel oil, and we have, at the very last, we have bitumen. We also have naphtha. Naphtha is f- in between the fuel oil and bitumen, you also have lubricating oil, by the way. And naphtha is after gasoline. So right here. So as you can see, as you go down the group of the fractionating column, what happens is the carbon chain enhances as carbon number increases, electron number also increases. If electron number increases, you will have van der Waals forces. Van der Waals forces, who are van der Waals forces, by the way? Van der Waals forces are basically your permanent dipoles and instantaneous dipole and temporary dipole. So your permanent dipole, temporary dipole, and instantaneous dipole, they're going to increase as the number of electron increases. So it's gonna get strong, it's gonna get stickier, filmier, because it's gonna have more interaction of attraction, and it's gonna get thicker and more viscous, sticky. It's going to get stickier. So the less viscous gas is refinery, and the most viscous chemical here is bitumen. That's why it's used in road surfacing. And this is one of the biggest reason. As the carbon number increases, electron increases, more temporary dipole can be set up, more induced dipole can be set up. It becomes really hard to break them apart. And as a result, what happens is they have a very high melting point and boiling point. But bigger chain chemicals like fuel oil, lubricating oil, they don't have much of uses. So the problem is since we can't industrially make big uses of like long chains, we have to crack them apart. What is exactly cracking? I'm sure you guys have heard about it as in on your O levels. Well, cracking is when you break longer chain down to make smaller alkanes and alkenes mixture. For example, if you have like decane, cetane, H22, we have a decane. It's a longer chain, and you want to crack them. How could you crack them? You can use aluminum oxide as a catalyst, and you provide a little bit of heat over here, and you need to give this aluminum oxide, which is acting as like a catalyst, to decrease the activation energy and speed up the reaction without being used up. It's going to break down into octane, and if you subtract 8 out of 10, 10 out of 8, you're going to get 2, 22 out of 18, you're going to get 4. So what is this? This is an alkane, and this guy is an alkene. So when we crack open a chemical, longer chain chemicals using catalyst and heat, you can get a mixture of alkane and alkene, and this process is called cracking. Now, Low molecular mass alkanes formed are good fuels and are always in high in demand. And low molecular alkenes are even better because they're very much reactive compared to that of alkane. So this makes chemical industry as a starting compounds for making new products, and they kind of become much more useful. All right. So that was all about the alkane revision part. If you still have any kind of confusion, you can just let me know about it, okay? Make sure that you thoroughly understand the free radical substitution part because that's one of the most important part of it. All right. Before I leave, I think I'm going to explain a little bit about catalytic converter because that also comes in the MCQs a lot. All right. So what are catalytic converters? Catalytic converters are essential in a lot of ways. Catalytic converters. So you see, to reduce the amount of pollutants released in cars' exhaust fumes, many cars are now fitted with catalytic converters. Well, they are very important because they have a precious metal called platinum inside them, coated in a very honeycomb shape to provide a larger surface area. So they have like a metal. That metal is made up of an expensive metal. It's platinum, and it's it's coated. It's the entire shape is of the converter is honeycomb. Why is it honeycomb? Well, and enhances the surface area. Surface area increases for that shape. Now, why do we need this guy? Well, catalytic converter is a very, very, very good converter because what it does is, you see, I told you in the very first part of the lecture that when alkenes are burning, they either produce carbon dioxide gas, which is like a problem to the environment, or if they're burning in an incomplete way, they can produce carbon monoxide, which is pretty toxic. Now, who you choose? I mean, one impacts environment, the other impacts your blood. Well, human decides to choose to not, um, for example, hamper them first. So yeah, we do care about environment, but then again, we have to save ourselves first, then we can also help the environment as well. So what happens is in this case, carbon monoxide has to be converted readily to carbon dioxide gas. So CO reacts with oxygen gas in the engine in the catalytic converter to form CO2. So I made a toxic gas to become a little bit less toxic. Now, then in the engine, we also produce nitrous oxide. The nitrous oxides are pretty bad because if they get out of the engine exhaust, they're gonna mix with the water vapor in the environment and they're gonna cause acid rain, and that's gonna be a lot of problem. So what we do is after forming the carbon dioxide gas, that's great. Carbon dioxide gas gets released. However, a little bit of nitrogen monoxide, however that forms, not nitrogen monoxide, when it's reacting with the in the engine at a very high temperature and pressure, nitrogen monoxide gets formed. It reacts with the carbon monoxide to form carbon dioxide gas and nitrogen gas. So carbon monoxide reacts with excess oxygen to form CO2, and carbon monoxide also reacts with the NO to form NO2 and N2. Well, if you balance it up properly, this is how it's going to look like. And in this case, we can see that nitrogen monoxide or nitrogen is being reduced and carbon monoxide is being oxidized. So this is a, what kind of a reaction is it? It's a redox reaction. All right, it's a redox reaction. Now, let's understand a few bits and bobs about this